Hello everyone, I'm Marlon Pierce from Indiana University. I'm going to be talking about Apache Aravatha distributed systems middleware to democratize and expand computational science with science gateways. So what is Aravatha? It's middleware to support science gateways, and I'll say more about what gateways are in a couple of slides. Aravatha is general purpose distributed task management software that's built on a microservice and component-based architecture. Aravatha provides capabilities to compose, manage, and execute and monitor large-scale applications on distributed computing resources. It supports execution on local clusters, national grids, academic, and commercial clouds. And it's multi-tenanted. One service runs many gateways. So that's great. But what is a science gateway? Well, it's a user-centric environment for conducting online computational science. As you could gather from the previous slide, we're typically talking about large-scale scientific computations. I decided in this presentation to make the spirit a little bit more casual instead of diving into computer science concepts in detail or the software architecture in detail. I instead wanted to provide a general introduction to some of these concepts. So I'm going to give you a somewhat silly question to begin with. What if Mark Zuckerberg read more chemistry and biology books? In 2003, 2004, Mark Zuckerberg and many others, of course, were building similar things, built the essential components of what became Facebook. And my question is, what if he were more interested in supporting scientific usage as opposed to social networking usage? Well, Facebook in its early days probably looked something like this, which is also the same architecture as many gateways today. There's a browser at the top. That's the user interface, or how the user interacts with the system. It's a web interface server, which interacts over an API, or I say SDK here, with a server that supports applications. So the application server, and these can be sometimes integrated with the web interface server, but the application server is the part that implements all the application logic. So for us, or for gateways, I should say, down at the bottom you see different supercomputers. So Big Red 2 is a supercomputer on our local campus. There's Stampede, Comet are computers here in the United States at University of Texas and San Diego Supercomputing Center respectively, and Eureka is a machine at Jülich Supercomputing Center in Germany. For Mark Zuckerberg, these probably were these are databases. So the interesting thing, of course, is that Facebook now has maybe 1 billion users, and it doesn't look like this anymore. Science gateways, however, still look pretty much like this. So our goal in Apache Aravatha, among other things, is to rethink how this architecture is put together and see if we can't adapt and adopt some of the lessons learned from cloud scale companies. So goal 1 for Apache Aravatha is to apply basic distributed computing concepts to science gateways. The screenshot, or the picture at the top of this slide, is a Google data center. It's a few years old. It may look nothing like this anymore, but this is the scale of computing these days. This is a cloud center. The problems of distributed computing, which may have been very theoretical decades ago when they were being worked out, are now practical, everyday, ordinary problems that have to be solved when you're working at the scale of a cloud company. And they don't have to be Google. It can be obviously a startup of any scale may need to still think about or be able to embed core distributed computing concepts into its architecture. Goal number 2 is to apply these new architectures, methodologies, and services to science gateways. So the picture here, the image is from Netflix's Chaos Monkey program. So this is a program or some software that goes out and randomly kills services that you have running. Well, if you think back a couple of slides, that what I have often called the octopus diagram, what a gateway looks like, that would not survive the chaos monkey. You kill that server and you're just down. How can we take lessons learned by companies like Netflix and Amazon and apply them to our science gateway architectures, our running software, so that they don't crash, or that they don't they're not subject to problems of local points of failure. So microservices and DevOps are a couple of buzzwords that are associated with these trends, and a couple of things that have been pioneered by companies like Netflix. So essentially, how can you run your software as a service or your platform as a service in an extremely resilient manner? And goal number 3 for Apache Aravatha is to adopt open source software practices such as open source governance. So the feather here is the Apache Software Foundation feather. Apache Software Foundation is more than just a license, and it's more than just, say, and certainly not a competitor to GitHub or something like that, but rather it is an organization that helps other organizations learn how to govern themselves in an open fashion. So in Apache Aravatha, when we took it to the Apache Software Foundation in order to become a top-level project, we did this in order to let everybody know, to send a signal that we are open for contributions in the form of code. I don't mean monetary contributions, but we're open for you to send your pull requests, your patches, and so forth, and help us make the code better. We want to build a community around Apache Aravatha developers, not just provide some open source software or some services that people take and use and never otherwise think about. So now let me give you an example, or a couple of examples of science gateways in action. So I'm going to talk about a couple of gateways that use Apache Aravatha. So the first is the Science and Engineering Application Grid, or CGRID, which is a web platform that includes both desktop and web user interfaces to help scientists conduct online computational science, molecular dynamics, material science, and so forth. So CGRID includes lots of tools, for example, to help you prepare input files for execution on high-end resources in the back end using well-known scientific applications. In this case, we show Gaussian. So you have visual editors for molecules, you have Gaussian-specific helper user interfaces to help you choose the right input settings, and various other tools that help you create your inputs for a particular problem. And then CGRID brokers that input file on backend resources that have Gaussian installed where you have access. So you can use this for real science. You can certainly also use it for real education. Here's an example paper that was published about a year ago that was enabled by CGRID. So the scientific question here is, how can I figure out the number of water molecules that that preferentially surround a calcium carbonate molecule? How does it hydrate? What does it look like? So this turns out to be quite a complicated problem to calculate, and you need multiple applications to do it, and you need to explore a fairly non-trivial parameter space. So the actual computation needed for exploring this problem is a workflow that looks something like this. So you are going to have an initial guess. Well, it's actually, I should say, you're going to start by putting one water molecule and one calcium carbonate molecule together and calculate the energetics. We'll then do this for 2 molecules, for 3 molecules, and so on. And I believe the authors here in the study went up to 18 or 20. Each one of those calculations goes through a workflow. You don't want to necessarily do the most expensive first principles calculation first, but rather you want to start with a molecular mechanics approximation. So that was done by the authors using an application called Tinker that is available through CGRID. This runs on Stampede, a supercomputer at the University of Texas. So from that, you can decide whether or not you want to go on to the next step. So the next step is to do a slightly more sophisticated calculation, or maybe more than slightly, using a code called DFTB plus to do density functional theory computations on that same calcium carbonate plus one or more water molecules, that same problem. You'll get a more slightly closer answer to the real situation through that computational technique that was also performed on Stampede. Now, at the end, for some of these, you're going to need to go from the first principles. So some of these computations you don't need to worry about. So the answer is not 1. You can probably eliminate 1 water molecule pretty quickly. You could probably also eliminate 18 water molecules or 19, so forth, pretty quickly. But some of these are fairly close, and you're going to need to do the full computation from first principles, preferably using the inputs from the previous computations. So that was done on Comet with code called Gaussian 09. So that was a real example of a real computation enabled by the secret gateway. It took place on several different supercomputers. It required a lot of computational time. It had a fairly large or non-trivial parameter space to explore. There are lots of outputs to manage. There are lots of applications that were brought to bear on the problem. This is a thing that gateways do for you. They broker your access to these resources. They help you manage your computations. They simplify access to a wide range of different computational codes. Another quick example, then I'll move on to look at Apache Aravatha in more detail, is the Ultrascan Science Gateway. So here is a gateway that supports the data analysis of analytical ultracentrifugation experiments. So the scientists here typically are not going to be users of supercomputers. They're more bench or lab scientists, but it turns out that the data analysis that they need is best done on supercomputers or clusters. So the gateway enables this, gives users a simplified interface for interacting with lots of different supercomputers. Ultrascan does its data analysis for users all over the world. It does it using supercomputers all over the world. So these are a couple of examples of science gateways. And there are some classifications of communities that you might want to think about if you're considering whether or not you want to run a science gateway yourself and use Apache Aravatha to do it. So you may be representing a university or academic department. You want to provide simplified access to your campus resources and help integrate those resources with national or international scale computing infrastructure. You may be running shared instrument facilities. You may be a participant in multi-site collaborations and virtual organizations. These could be funded or unfunded. But you have groups of scientists who need to collaborate using a common pool of resources. These don't have to be academic, of course. Many of the computational applications that we focus on are of interest to the businesses and commercial sector clients. So You might want to provide software as a service for a particular application suite that your company provides, or you might want to use them internally to increase the efficiency of your research and development staff. And of course, lastly, you might be a member of a small research group where you want a gateway that can preserve the work that is done by the students, postdocs, or members of a class that you might be teaching. So let's map some of these gateways to Apache Aravatha. So I'm going to work from left to right here. So on the left you have at the bottom user communities, and I think we've given examples of a few of those. You also of course have the gateway providers like Cgrid or Ultrascan, and they interact through a gateway user interface. This user interface could be desktop or web interface. It may be built in a large number of different ways. In Apache Aravatha, we have a reference implementation called the PHP Gateway for Aravatha, or the PGA. The Cgrid uses this, but Ultrascan doesn't. It's just a choice. You're going to need something, so you can build it yourself, or you can use something we provide. So this gateway, or the front end, talks to Apache Aravatha using remote procedure calls or remote invocations. So I show here in the middle PHP SDK. So that is, if you will, software development kit is SDK. Apache Aravatha provides an API and different language bindings. So if you have a PHP gateway, you use the PHP language bindings for our API. You don't have to just use PHP. As I'll say in a minute, we provide SDKs for a lot of different other programming languages. So the middle section here, inside the box, you see the Apache Aravatha server, which itself is composed of lots of different components, and includes other third-party components that help it run at scale. These include Zookeeper and RabbitMQ, which help us keep services up and running and help the services communicate with each other. A couple of other components include the credential store and experiment and app catalogs. So these are things that help manage security credentials as you talk to remote resources on the far right, and things that help capture the metadata about what a user might have done. So what code did they use, where did they run the job, what input parameters, where the output files are, those sorts of things. Finally, on the far right, you have the computational resources. I've talked a little bit about those already. We particularly target clusters, supercomputers, computational clouds, things like that, because we are typically focused on helping users make the best use of well-known community and commercial applications. So let's look in this, go back a minute. So let's take this central square, the Aravatha server, and look at it a little bit more detail. Let's blow it up. So again, we're going to work from left to right. Users come in through lots of different user interfaces. They can be, for Aravatha, they can be developed in lots of different ways, lots of different programming languages, because we have an API server that is implemented with a sister project called Apache Thrift. So Thrift gives us a way of defining a programming language interface definition for our APIs and our data models. And we can provide SDK bindings for our API using Java, C++, PHP, Python, so forth. The API server is, again, just the front door. The other components include the orchestrator, which is the brains of Aravatha and is going to be responsible for things such as internal scheduling. Going over to the To the far right, you see the application factory. Historically, we call it GFAC. So this is the component that interacts with remote resources, and it provides the proxy to lots of different computers or resources using lots of different techniques. These days we preferentially use SSH, SCP for remote communications, but we can certainly accommodate others, and we run right now lots of other middleware clients within the application factory, including Unicore, GlobusGram, and other cloud interfaces. A couple of other components to draw your attention to. One is the messaging system. So this is where the components communicate with each other. We implement this with RabbitMQ. We can also accommodate external messaging, which might come from remote resources that also can publish AMQP compatible messages, and we can also use the message system to send out messages to clients external to Aravatha that also subscribe. Workflow engine is a component that handles workflows such as we saw one earlier for cgrid, where you have multiple components that need to interact with different resources at different steps. So you want to define the rules for how a multi-stage computation could take place. And finally, at the bottom, we have the application experiment catalog. So we call this the registry component within Aravatha, and this has lots of different subcomponents, but in a sense, essentially it stores all of the metadata about computing resources, applications, experiments that people have performed, and so forth, and makes them persistent, makes them searchable, and makes them accessible to other components. So that's Apache Aravatha, and it's open source software. You can take it, you can use it, but we also depend upon lots of other, to run it as a production service, depend upon lots of other components. I mentioned a couple of slides previously, Zookeeper and AMQP messaging systems. Another is a WSO2 identity server. So to run the full stack is a thing that requires several different components over and above just Aravatha, and it's useful for us to think about how to run all of that stuff as a common multi-tenanted service for lots of different gateways at the same time. So our motivation for doing this is to think about how we can help Aravatha scale up without necessarily having one consultant per gateway. So how can we make, in our own team here at IU, how can we make our support staff more interchangeable and able to help lots of different gateways without needing to know lots of information about the specific bindings that might exist between a gateway client and the Aravatha middleware. So this is what things look like in a little bit more detail. So you have lots of different gateways that we are working with to interact with SciGAP services. So SciGAP services might include Apache Aravatha or its core components I've illustrated earlier. They might be API calls that help interact also with other services that we have in our software stack, such as the API server, such as the identity server or messaging bus and so forth. We have obviously a programming interface for all of these things, and these interfaces support both regular users and administrative users. The core capabilities are things I've illustrated before: identity management, workflow and job management, data, metadata, and provenance management, monitoring and auditing, and then the software itself supports access to lots of different, or potentially supports access to lots of different back-end resources, as we see at the bottom. So this is the same slide at the beginning, almost, except at the top, you have lots of gateways connecting simultaneously to the running service. So it's not just running software anymore and providing software for people to use, but it's running a service that lots of people can connect to at the same time. I'll close with, again, a mention of Apache. So here is a list of our PMC members and committers. All of these people are members of the Apache Aravatha project. Some are active and some are not. That doesn't matter. In Apache world, merit is earned and never lost. If you are a contributor and contribute to Apache Aravatha, you will eventually get acknowledged and elected as a full-fledged member of the project, which means that you have write access to the trunk of the code base, but also it means you have, if you're a PMC member, full voting rights to determine important directions and activities of the project. Our motivation for doing this, again, is to encourage people to get involved in the codes, the open source codes that they like and use. Don't just take them, but give back to them, and have a code base that you feel like you're an owner of, and a code base that you feel like you don't have to reinvent, but rather you are a full-fledged member of the project. You can contribute to that code and extend it in your own customized ways yourself. So thank you very much for your attention. If you want to get in touch with us, I encourage you to do so through the Aravatha mailing list, either the dev or the users list. And you can also feel free to contact either my colleague Suresh Maru or myself. And I thank you for your attention.